And I'll go through the notes more commenting maybe what's happening. And generally, I'm mostly interested that you kind of feel how things change when we change environment. How do we define domain differently? How do we look at different relations? And so on. This was the story about the that we already covered. But so far, I only mentioned one quantifier, and that is if I have some statement q of x, then we talk about for every x, q of x, which is what? This statement is true if in the whole domain, whenever I plug in x, statement is true. There is any other one that works the other, like E upside down. What about that? Not left, right, inverted. What would that one be? It's called existential quantifier. And when is that true?
When one is true.
When one of them is true. So if you can find a witness that that one, even if there's more than one, first one that you found is called the witness of truth of this statement. So this is existential. And this is universal. They're also making bound variables. So I told this whole story with universal. With the existential, everything works the same way, just that one difference. Let's look at this example on the screen. It says the following. So phi of x is the following statement. By the way, if you notice, I put here some column. I won't be always that careful, but generally, when we want to precisely, when we put a column here, that means I'm not saying equal like equal numbers. There is some meta-equality and formal equality. This is so-called meta-equality. I'm saying phi of x is this. This is not mathematical equality that you need check. I'm assigning it. So I'm saying phi of x for what? And now I explain for what. There exists x from z such that x squared equals 16. Sometimes you see in the existential or universal quantifier, we specify the domain. So instead of saying it on the side, we specify it here. So let's explain every symbol. This is existential, as we say. This is the symbol that we'll mention more in chapter 3. This is belongs, or from, in this statement. So there exists x from where? From z, and so I'm specifying domain, and not on the picture, but just saying from where it is, such that x squared is 16. Yes? At least one. That's what it means. So here it is. And this one actually says, that's actually the same story about exclusive or. Because existential is really or, universal is and. First one has a property, and second one and third one. So think of universal as long and existential as long or. So, if you look at this, how do you check the truth of this statement? Forget exists x from z. Is this a statement first, yes or no? Is this a predicate? And then what? You need to plug in x. But here I'm saying, I don't care, I don't wait for you to give me x. What I want you to do to tell me if you are able to find x to make this true. So what? If you find me such x, that's it. Statement is true, you gave me a witness. If somehow you show me that running through all the integers you are sure that you will never get this, then it's false. So for example, for this one, true or false? True, give me witness. Could it be another one? I don't care, give me one, done. That's what you ask. So we need one witness. From there on, we don't care. Sometimes people write there exists only one, and that is, and that's, but forget that. It is one in the index or one with the exclamation mark. If you ever see it, don't be surprised. Yes?
Is that just an equal sign before
No, this is just assignment symbol, and that's used in computer science as well. I'm assigning that phi of x means this. So this is really, so that's why I said it's a meta symbol. My story about it, and it's not part, this is formula. This is formal language, and this is meta language. So computer only sees this, and this is our story. This object in mathematics we will call phi of x, and that assignment process is usually written like this, and you'll see it in pseudo-programming. Yes?
So that's just assigning x a specific value?
Which one?
Phi of x.
No, phi of x just says this, is this a formula, yes or no? Yes. And then this formula, I will just give it a name and I will call it formula of x. Although, is x free variable or bound variable? Bound. Actually, I didn't even need to specify x. I can just, phi is the name of this formula. And you tell me true or false. All right. Let's see a little more, just more examples. What about this one? Psi of x is this. There exists x from z such that x squared equals 19. Is this formula true or false? False, but this will be a little trickier because now you need to deny all the possible candidates. And so how do you deny candidates? False. Why? And that's a little trickier. How would you justify to someone that this is false? Give me an argument. Why is this false?
Assume it's true. 4 squared is 16.
No, I would just try all the possible candidates and deny them. So generally what? What if x is 5 or bigger? Could that number work? Why? Or you can say, or if someone gives me a witness A and that A is greater or equal to 5, then what happens? A squared is greater or equal to 25, so A squared cannot be 19. Do you agree? What else? Yes?
Is that symbol in the setup? Do you have existential in the set of z?
What one? Oh, there exists X from Z. Yes, so this is from. Or belongs.
We're assuming z is integers.
Yes, yes, of course. Z is always, when mathematicians talk, you don't need to explain who is Z. Z is integers. Okay, Z comes from this. Zahlen, German word for counting. Or number, yes. Numbers. Yes. All right, so so here it is. If x is A, and here it is. I say, I deny you possibility to bring me a witness. So I say the following. If you give me witness above 5, it'll be too big. Do you agree? If you give me witness below negative 5, your A squared again will be greater than 25, so cannot be 19. Make sense? I denied tons of witnesses. What are your only witnesses left? Those between negative 4 and 4. But if you try any of them, your A squared will be what? Less than 16. So can you get 19? No, I just denied all your possible witnesses, like bulk denial. Instead of going one by one, I actually, all above 5, of course. Do we need to agree on the knowledge of integers that I used here? So that's a knowledge of discipline, but here is how I kind of provided the argument covering all the possible cases. If you give me a witness above 5, you'll get too much. Below negative 5, the same thing. Between negative 4 and 4, too little. There's no way you will reach. Sometimes students like to say here, no, my argument would be square root of 19 is not an integer. But integers have no idea what are you saying. Imagine that you have a system that doesn't ever saw what square roots are, you see. So you have a system that's only programmed to do multiplication and addition, and you cannot use fancy language there. So square root is just what do you mean? So that's not introduced here. Only thing is integers, addition, multiplication, and you have to talk in that language. Yes?
Could you take 19 and do like it's only divisible by 1 and 19?
No, not because of that, because it's not perfect square. Because you see here I took 16, and easily it is a perfect square. 19, of course, there's no integer that does that. So I wanted to kind of provide the structure of that reasoning. So how do you confirm existential, and how do you what? Deny existential,
But
yes.
What she was saying was that since it's a prime number, it can't, because there's
Even if I did 18, reasoning would be the same. So it's not about primality. It just happened to be. I just did it, So it's not primality. I would like you to see about it perfect square or not.
But that would deny it being a perfect square as well. It would be a case against it.
I agree. Prime number is never a square, something like that. But this needs probably a little more knowledge. What's prime and so on and so on. So I agree, but you're pulling more from it, and also, I like more the argument that I provided, not only because I provided, but it's also because it works when you change to 18, and you have to change the argument will keep the same one. So it's more like, generic type. All right, and here, there is something here about universal conditional statement. What would that be? You see, look at this statement. For every x from R, if x is greater than 2, x squared is greater than 4. R is the real number. Whenever you do this R, we assume real numbers. So, example 214 actually tells you the following. For every x from R, x is greater than 2 implies x squared greater than or equal to 4. Is this correct? Is this well-constructed statement? Yes or no? Let's say, is this basic statement, x greater than 2? And this is the basic statement. And then I do logic, close it, I do universal quantifier. That's how you want to write statements. By the way, remember, I never quantify predicate. And I see that students like to do that. So I only quantify, remember, variables only actually. So for every x, and then I sometimes say for every x in R. This statement, how do I see it? My domain are real numbers. Feed whatever you want. Do you agree? And then I'm saying here, feed whatever you want. And if it is greater than or equal to, I guarantee the square will be greater than or equal to 4. Do you agree? Sometimes we can say this a little differently. Because this only talks about numbers that are greater than or equal to. Do you agree? Because if numbers less than 2, this will be true anyway. So here's what I can do. I can make a little simpler structure at the expense of reducing the domain. So generally, instead of talking about all real numbers, I will only talk about real numbers that are greater than or equal to. Those, I don't want to even talk about them. So my domain are not all real numbers. Who's my restricted domain? I'll call it D. Who is in my restricted domain? Only real numbers that are what? And then how would I say that now? For every x from where? Not from R, but from where? D, what's true? So generally, by restricting the domain, I simplify the structure of the sentence. And that's what people do very often. So sometimes construction on the domain works for the sentence, for simplicity of all of the sentence. Here is one very important example. Sometimes I do assign that on the quiz, and we can learn a lot from this example from geometry. And maybe you saw this in geometry. And this is where you actually build your domain, and you have to be very careful about it. So this is a good example. Let's be focused on it and talk about it in more detail. So here it is. I'm working on geometry, and I want to write precise mathematical statement about these objects. So Here it is. First, I want to fix my domain. So who's my domain? Geometric objects, because that's what I want to talk about. And what do they discuss in geometry? Points. What else? Lines and planes. Those basic, and later on triangles and all this. But when you look at the Euclidean axioms in the beginning of geometry, first set of axioms talks only about that. Points, lines, and planes. That's like the simplest thing that exists. The same thing in Calc 3. If you're having Calc 3 now, then you know that section that talks about lines and planes in space. All right, so who do I need there? Points, lines, and planes. Do you agree with me? Here is the trick, that I don't have one type of objects. Numbers, all numbers. That was nice. Integers, all integers. They all behave the same way. Here I have three types of objects, and they behave very much differently. You cannot say a line belongs to line, but you can say point belongs to a line. Do you agree? So whenever you talk about object, either if I give it a name or if I treat it as variable, your first question is, tell me, what does that variable stand for? So let's see how I will record this. For every two distinct points, there exists a line containing them. So it says for every two distinct points. What am I talking here about? Am I talking about 2 points, yes or no?
Is it at least a line?
What say?
At least a line.
There exists a line, that's it. Yes, there exists a line containing them. So here it is. Don't rush your sentence. First try to break it, maybe rewrite it into simpler form that will give you an idea how do you label it. So what? Here it says the following. Start with two objects, because it says for every two points, do you agree? So start with two objects. Tell me what they are. So those two objects that I start with, I will call x and y, because they didn't say two specific lines. They have for every 2 points. So here it is. In order to accomplish this, I'll write the following statements. I'll call those objects x and y. So I'll say the following: for every x and for every y. Do you understand why I wrote for every x and for every y? Those are, I took x and y as the name of my two objects. Because if you write every x and every y, those are two objects from your world. What is the first thing to specify? If you don't tell me, I can think that x and y might be lines or planes, but you are saying that x and y are what? So you have to have a predicate telling me. So there must be a predicate that says predicates. You must have them in the language. Predicates for what? Being a point, being a line, and being a plane. And I give them the name. Point, P of x, line, L of x, and a plane, let's say, S of x. Do you understand that? So now I'll have a language whenever I introduce variables to say immediately what I think that they are. So we'll say the following: for every x, for every y. What am I assuming about my objects? Are they something specific? Are they both points? So if P of x, so if x is a point and y is a point. So far I said for every two objects that are both points, what happens? Implies that there exists an object I'll give it a name z such that. But look at this quantifier. This could be done for any 2 points. For any 2 points, there exists a z. What do I need to tell you about z now? What's so special? What is z first? Line. So z such that. And look at this. I say there exists a z, and now I'm starting z description. Whatever I say, it's in the parentheses. The moment you close the parentheses, you change things. So there exists z, and now z story comes. And I close the first parenthesis, and I'm done. Tell me everything that you want about z. Z is what? Line. And what else is special about that z? What are they saying?
And point X and point Y belong to.
Yes, so generally I need also belonging. That's usually in set theory. We know that's what? X belongs to Z and Y belongs to Z. Here it is. This is how we write this in a predicate calculus. Yes?
Can all that stuff in the brackets be simplified to x, comma, y in L of z?
Not in L of Z, because you see, here it is. X, comma, Y in L of Z. And that's very important for you as a computer scientist. Type of the object is the crucial thing. If your type is not good, nothing makes sense. Look at this. What's L of Z? Is that line or that's yes, no?
L of,
Z is the line. L of Z, remember, that's a predicate. Predicate only has output what? Yes or no. So can you belong to yes or no? No, you cannot. You belong to a line. So what's the name of the line? So you can belong to Z or not belong to Z, but you cannot belong to L of Z. Is that clear? Because you cannot, because L of Z is just a predicate. So you say that Z is line, and then the same thing here. I see very often here, for every point, people say this, for every P of X, for every P of Y. This is also nonsense. Why? Because you never quantify a predicate. Who do you quantify? Only objects. There is some called predicate calculus of second order. We don't study that. So remember, so introduce as many variables as you want, and then say, introduce their names and talk about them. It's always between the objects, and never between the relations. Even in the beginning, if you are confused how to construct the sentence, don't go into too many details. You can say the following. If this is too much, you can say the following. For every 2 points, if X is a point and Y is a point, then there exists Z such that U of X, Y, Z. This is again, is this correct statement? Yes, it's too vague. I didn't specify, but it's correct. What does it say? For every 2 points, there exists an object that's somehow related to them. So that's what it says, but it's correct. It's too vague. I can say it more, but as I said, if it's too much to go into full detail in your sentence, say it vaguely, but say it correctly. So for example, I can do better and say P of X and P of Y implies there is this Z such that Z is the line and U of X, Y, Z. Is this a little more, yes or no? Now I'm saying not only the 3 objects are related, at least I know that what? First 2 objects are points, and the third object is what? Line. So here it says X is a point, Y is the point, and for them I can always find third object who is a line, and they do something together, whatever that is. And then if you specify at the end what is it that they do together, then you have very precise way to say your statement. As I said, it doesn't come quickly, so this is what you want to see. Your rough structure has to be right, and then you can feed more and more detail. Whenever you're not comfortable writing a sentence, write it generally and see if you have general structure, and then go with more details. All right? So here it is. Q of n is a factor of 8, n is a factor of 4, S of n is less than 5, and n is different from 3. And then we said use the equivalence relation, use implication equivalence to express the relationship between P of n, Q of n, and R of n. So what is this? If number is a factor of 8, does it mean that it's factor of 4? That's not true. So for example, so what? We can say the following. So Q of n stands for what? N is a n divides into 8. R of n is n divides into 4. And S of n is what? N less than 5 and n different from 3. I very often like to ask questions like this. You can see on the old exams. I want you to see if you understand what you are saying or someone else is saying about those. Who do you imply who? So do you think that Q of n implies R of n for every n? Is that true or not? True or not? If you say false, you need to give me counterexample. The one where my statement fails, who's your counterexample? 8. Because 8 does divide into 8, so this is true. So your counterexample, very nice. N equals 8. Why? Because Q of 8 is true, and R of 8 is false. So you have true implies false for that particular n. You gave me counterexample, and my universal statement is not true. Very nice. So false altogether. What about for every n, R of n implies Q of n? Is that true? If you are factor of 4, and 4 is factor of 8, are you also contained in 8? The answer is yes. So true. As I said, now a little more writing for evidence, what I just said. So that's a little knowledge of it. You say, whatever number you try, or you can list. Who are the only factors of 4? That's easy. Who are the only candidates? Factor of 4 are what? 1, 2, 4, and they're negative versions, but negative always behaves like positive. Are they also factors of 8, yes or no? So this is short list. Sometimes if a list is short, you just run all the examples and then show the statements through. What about S of n? S of n says number is less than 5 and it's not 3. How is S of n, how are these two related? Oh, by the way, I didn't read that. What is the domain? Always be careful about domain. Is it Z or Z plus? Z plus, only about positive. So domain is Z plus. So Z plus is just positive numbers, 1, 2, 3, 4, and so on. So in Z plus, S of n, who are the numbers that satisfy S of n? That's called truth sets. So what would be the truth set for S of n? Numbers below 5, but not 3. So it's a 1, 2, skip 3, and write 4. Do you agree? What is the true set here? True set here is what? Factors of 4 are 1, 2, and 4. And truth set here is 1, 2, 4, 8. So what is this telling you? Are R and S true in exactly the same cases, yes or no? So what can we say? For every n, what do we have? that R of n is what? Equivalent with S of n. They are either both true or both false. They are true on three numbers. Which are the numbers? 1, 2, and 4, and not on the others. If you look in our plan, I plan to cover sections 2.1 and 2.2. There's no way, there's no reason to start thinking about 2.2. We'll leave 2.2 for Monday, so you don't need to look at it. And I think we'll cover 2.2 and 2.3 on Monday. So let's just smoothly finish section 2.1, which is much more important to introduce properly. There is one more thing. There are a few things to do actually left in these 6 minutes. We want to learn how to do negation of the quantifiers. And can you see how do we do negation of a quantity? Can someone comment on what we see on the screen? All right, good. Let's try to give them some sense. So here it is. If you have a segment, I'm not going to write from D. I'll just write for every x, q of x. What is this? Is this universal statement? Yes or no? What if someone writes negation in front of it? And here's how negation goes through it. It travels inside. When you cross every, that becomes exist, and negation attaches to q. This is the rule. We need to memorize it and use it quite frequently. First, does it make sense?
It does not exist.
If you are saying that not everybody is good, what are you saying? The same, there exists someone who's not good, do you agree? Basically, this is just colloquial argument. By definition, you can see that those are true. So if this is true, then left side is false, and this one is also false. And then if this is false, this is true, and this is also true. By the way, the reasoning is also, what is this? This is generally the same as infinite De Morgan's law. Why? Because didn't we say that universal quantifiers means for everybody? So first and second. So you can think of this as negation of, like, q of 1 and q of second and q of third and so on, although infinitely many. How would De Morgan go through this? It would be what? Negation of q of 1 or negation of q of 2 or negation of q of n or infinitely. What would that be? The junction is what? There exists x such that what? Not q of x. So we often call these rules De Morgan's rules for quantifiers. So when negation goes through universal, it makes it what? Existential and attaches as negation to inside statement. How does it go through negation through existential? Makes it what? Yes.
How would you say that there's no values of x?
No, you are saying the following. Here you are saying there is no person in California that's taller than 7 feet. It's the same thing as saying that everybody's California is below 7 feet. Is that the same statement? That's what it says. So generally, that's colloquial kind of reasoning for it. Again, it's you can check through it left and right, and then see it very easily. So, for example, in this statement that we see on the board, it says, how would you do negation? There exists an integer larger than 5. What would be negation of that?
There's an integer that is not greater than 5.
So, but it's nicer if you go with that negation. So negation of there exists is what? Every integer is what? Below 5. Yes, there's nobody who's larger than 5. That means everybody is opposite from that. So everybody is below 5. One more thing. and that is, okay, these are just examples. How would you say negation of this? The difference of any two irrational numbers is an irrational number. What would be the negation of that? I wrote it there: for every irrational x and every irrational y, their difference is also irrational. What would be negation? There exists x, irrational, and there exists y, irrational, such that their difference is what? Rational. And is that true? Yes. If you take square root of 2 plus 1, which is irrational, and subtract square root of 2, what do you get? 1, which is very nicely rational. So it's really negation is true. So that's one of the things you need to practice, how to say negation of a statement. And then two more details. All right, I'll skip this big slogan of a revolution or a pre-revolutionary period. You all remember this statement? No taxation without representation? All right, so how do we record that, for example? In the world of people or population of United States in 18th century or anywhere, they actually talked about anything in any world, in any population of the world. We shouldn't have a situation or a man or a country, so there shouldn't be a person who pays the tax and it's not represented. Is that what it says? And then when you go with negation, what happens? Negation of exist, what does it say? So here it is now. So you record it carefully and then you start running machinery. So it says, for every x, negation of t of x or r of x. Do you agree? Because when negation came in, then I use De Morgan and get negation becomes every, gets non-t or not r, which is just r. But then you recognize, do you recognize this structure? Who is this? Not p or q. P implies, so we get for every x, t of x implies r of x. So now we can say it in which way? Every person that pays taxes should be what? Represented. And we agree with that. So that now we understand it better. What is it that they said? It was too much coded or said into too simple way. And then here's one very important thing to do at the end. I know we are on negative time already. So, and that is vacuous truth of universal statement. That's very important to be aware of that because sometimes it is confusing. So what is that? What can you say about the population that has no members? Like, for example, what can I say about all people in California that are taller than 10 feet? Can I say that they are green? Yes. Can I say that they are blue? So I can say about them whatever I want and it's true. If the set is empty, you can say anything you want about it and that's considered true. So that's called universal truth of a vacuum statement. Why? Because look at this. If I say for every x from certain domain when there is nobody, phi of x. And we always say that's always true no matter what say if D is empty. Why? Because what is negation of that statement? There exists x from D such that not phi of x. Can you ever give me a witness here in that domain? You cannot. So since you can never give me domain, this is for sure false. So if your negation is false, it's reasonable for you, even it's artificial, to assume that you are true. So remember, whenever I see the domain is empty, everything is true, anything goes on those sets. And as I said, try to make yourself convinced. If not, Just let's discuss it more. All right, so that's our section 2.1, and then on Monday we'll talk on 2.2 and 2.3.